now we're going to learn how to include the errors into your calculations. So let's say that you have you take two measurements. So the first one is going to be x, and let's say that's going to be your best estimate for x, and plus or minus the error in x. And let's say you take another measurement, y, and you're going to write that as the best estimate for y, plus or minus the error for y. So these are going to be your measurements. And using those measurements, you're going to perform calculations. So what that means is that you're going to get some calculated value. I'm going to call it v. And that calculated value is going to depend on both x and y. So v is going to be some function of x and y. So how can we include the errors these errors here into the calculated value? So first thing is that you're going to find, well, pretty much just plug in the best estimates into your calculated value. So I'm going to call that your best value is going to be just your value with the best estimates for x and the best estimates for y plugged in. So that's going to give us our best estimate for the calculated value. And it's just going to be take your values for x best and y best, plug it into the formula, and that's going to be your best estimate for your calculated value. But now though, what is going to be the error for that calculated value? That's going to be the most important part. So how can we find that? And in reality, there are actually a wide variety of ways to get this error. It depends on what the formula looks like. But I'm going to give you one simplified version that applies in pretty much in most cases. And it's based on a fractional error. So we're going to say that the fractional error of your calculated value is going to be the error in the calculated value divided by the best estimate, or your best estimate for the calculated value. That's going to equal this thing here. It looks like the Pythagorean theorem. It's going to be and inside the Pythagorean, it's going to be one number squared plus another number squared, because there's two measurements here. So here, and what gets squared is the fractional error for both of your measurements. So it's going to be the fractional error for x and the fractional error for y. So this is the most general and a formula that's going to apply in most cases. It actually turns out that error analysis sometimes winds up looking like an art, where you have different formulas for different situations. But this one here is going to be pretty applicable, which means that the error won't be it won't be the best. This is not going to be the best way to calculate the error in every case, but it works in most cases. And for this class, I think this is going to be suitable. If you're going to take more advanced, if you're going to do very advanced experiments, you'll have to use more advanced methods. But for an introductory class, this should be good enough here. So now, though, you can actually go add another layer of precision or of accuracy by using this formula. So, but I think you're probably going to use this one more often, though. But if any of you want to use this version, you're welcome to try. So the fractional error can also be written as a square root of some number squared. I'm going to have to make this thing fit here. So the fractional error of your measured value if you can use calculus and this could increase the accuracy of your error. So it's going to be defined like this. Is going to be the partial derivative of the measured value respect to x multiplied by the error in x, or multiplied by the fractional error. So all this is calculated at your value for the best estimate squared, and then plus the partial derivative of your value with respect to y, and then multiply by the error, or multiply by the fractional error. So that's going to be the error in y over the value or over the value of the function. And here again, calculated at the best estimate squared. So this one is going to give you more accurate, a better value for the error, but this one is pretty general and easy to apply and probably easier to remember. So I think you'll be using that one more often. Here we're going to learn how to compare our measurements to accepted values. So let's say that I'm going to write this, do this along a line. So let's say that you have an accepted value. I'm going to call that VAC for accepted. And let's say that your best estimate is, it's not, they don't match, so that there's some separation between them. And this is going to be your best estimate here. So we're going to define, first of all, the discrepancy to just be the difference between the accepted and the best estimate. So I'm going to say that delta V, which is called the discrepancy, that's going to be, actually you can take it to be the absolute value, but I like to leave it with, take it without the absolute value. So it's going to be the best estimate minus the accepted value. So we're going to call that one the discrepancy. And so usually though, if you're comparing your best estimate to an accepted value, you don't write the discrepancy, you write this as a percent, or we're going to call this a percent error. And we're going to find the percent error formula to equal this. It's going to be the discrepancy divided by the accepted value times 100. So this is going to be the percent error. So this is when you're comparing your accepted value, so when you're comparing your measurement to an accepted value. And there's something very important here. The whole idea is this, is that no experiment is ever 100% perfect and accurate. So what that means then is that the percent error should never be zero, because in everything there's always going to be some kind of error in the experiment. So another way to say this then is this. So if you do get an experiment where your percent error is zero, so if you do get an experiment where you do your calculations and you get 0% error, what that's telling you to do is to redo your experiment with smaller errors. With smaller values for the error. So just go to the next decimal place. So it's never satisfactory to write, that your percent error is zero. That is not satisfactory. You always want to, if you get 0% error, that means you have to redo the experiment with a smaller error, so that you get a non-0% error. So we're going to apply this to something similar. So now you can actually, instead of comparing your measurements to an accepted value, you can compare two measurements. So let's say they have a value 1 for you take a measurement, you have value 1, you take the measurement again, you have value 2 there. And how can you compare these two values? So it's something similar. We're going to find the discrepancy in this case here. It just be the difference, which will be value 2 minus value 1. And here, what we're going to say is that this is going to be the error in this case. We're actually going to call it the percent difference. So we're going to represent how far apart these two numbers are by what's called the percent difference. And the percent difference is equal to the discrepancy divided by the average value times 100. So remember, the average in this case here, if it's two numbers, it'll just be value 1 plus value 2 divided by 2. And something else is that percent errors and percent differences, they can be positive or negative. Some formulas write them as positive, but I prefer to leave them as positive or negative because if you can get multiple percent errors that are all negative, it can indicate that something is off. I think it's best to just leave, not include the absolute values when you're calculating the percent errors or percent differences.